Hello, everyone. I am going to present the paper entitled Adversarial Transfer for Named Entity Boundary Detection with Pointer Networks. Named Entity Recognition, NER, is a fundamental task in natural language processing which aims to jointly resolve the boundaries and type of a named entity in text. For example, the entity, Michael Jeffrey Jordan, is a person in this sentence. In this paper, we ignore the entity typing and focus on the subtask of named entity boundary detection, which involves detecting the start and end boundaries of an entity mentioned in text. Why do we focus on named entity boundary detection? First, errors made in entity boundary detection inevitably mislead and adversely affect subsequent entity typing systems. Second, there could be conflicts between the types predicted by NER systems and the types of the entities disambiguated through the entity linking process. To the best of our knowledge, existing work is designed for NER, not specially for named entity boundary detection. This has created an overwhelming demand for more accurate and robust boundary detection approaches. Thus, a more accurate and robust detection approach is desired to alleviate error propagation in downstream applications. Off-the-shelf NER systems suffer from this shift in data distribution from the actual data encountered at test time, resulting in poor performance. These systems also cannot effectively leverage target domain data. Based on the motivations mentioned above, in this paper, we focus on named entity boundary detection. More importantly, we also focus on an extreme case of transfer learning, unsupervised transfer learning. The main advantage is that unsupervised transfer method does not require any annotated target domain data. In this paper, we propose AT-Bdry, an adversarial transfer approach for named entity boundary detection with pointer networks. The left side figure shows the architecture of our approach, which consists of 4 components: input representation, context encoder, tag decoder, and domain discriminator. The input representation in our model consists of character level and word level representations. In the context encoder layer, we use a bidirectional GRU network to memorize past and future information in the input sequence. In the tag decoder layer, we integrate a pointer mechanism into a sequence labeling framework. The aim of the domain discriminator is to encourage domain invariant representations. It is worth mentioning that no annotated target domain data is necessary in our framework. We proposed a novel sequential labeling model, which resorts to a pointer mechanism to detect named entity boundaries based on intermediate representations by the context encoder. As a result, which can effectively handle variable size vocabulary in the output to produce entity boundaries depending on the input sequence. This figure shows the architecture of our sequential labeling model. The input sentence is, Michael Jeffrey Jordan was born in Brooklyn, New York. After the input represent layer and context encoder layer, we can get the hidden states for each word. In the pointing phase, the decoder detects entity boundaries only if the current input is a start boundary. Otherwise, it will switch the decoder status to inactive and no boundary will be detected. For example, given the word Michael, the decoder determines its boundary at word Jordan. Then the word was as input, the decoder determines that this word is not a start of an entity. Finally, our approach detects 3 entities: Michael Jeffrey Jordan, Brooklyn, and New York. In particular, in order to encourage domain invariant features, we seek the parameters θ(f) that maximize the loss of the domain discriminator, by making the 2 feature distributions as indistinguishable as possible, while simultaneously seeking the parameters θd and θf that minimize the loss of the domain discriminator. In addition, we seek the parameters θt that minimize the loss of the tag decoder. Thus, the optimization problem involves a minimization with respect to some parameters and a maximization with respect to others. This mechanism results in the emergence of extracted features that are discriminative for sequence labeling on the source domain, and indistinguishable with respect to the shift between source and target domains. We use 5 popular benchmark datasets to ascertain the effectiveness of our approach. Because our task is boundary detection, we ignore entity types in all datasets. This table shows the statistics of the datasets. The first 3 datasets are formal text. The last 2 datasets are informal text, which are from Twitter. We first evaluate our sequential labeling model on in-domain entity boundary detection. That is, we fully train our boundary detection model onto a Notes 5.0 dataset and test on its standard test dataset. The results are summarized in Table 2. First, our boundary detection model outperforms all baselines in terms of precision, recall and F1 scores. We attribute this to the fact that our approach resorts to point networks, which can effectively capture the dependencies of input sentence when the entity boundaries are sparse. Second, the performance of Stanford NER is poor. This observation coincides with our previous claim that off-the-shelf NER systems are not specifically designed for entity boundary detection. For better understanding, we visualize pointer attention weights with an example in Figure 3. The words on the y-axis are the input of the GRU decoder. The words on the x-axis are the input of the GRU encoder. Observe that the identified boundaries have dominant attention weights, which implies that our approach can successfully learn sentence features for entity boundary detection. We consider one formal text data, for example, Cohen LLO3 as the source domain, and another formal text, for example, WikiGold as the target domain. Table 3 reports the performance on standard test sets of target domains. From the results, we have the following observations. First, our approach significantly outperforms all baseline methods to date. Second, with the adversarial transfer mechanism, our approach significantly improves the performance of training only on source datasets. NER informal text is well studied and the performance of many existing models drops dramatically in informal text. In this experiment, we investigate the effectiveness of our approach when the data distribution gap between the source domain and the target domain increases. Therefore, we choose formal text as the source domain and informal text as the target domain. Table 4 summarizes the results. From the results, we attribute this to the fact that our approach can learn domain-invariant representations, which can effectively reduce the distance in data distributions between the source and target domains. In our approach, the adversarial transfer component plays a role in encouraging domain-invariant representations. In this experiment, we investigate the effect of adversarial transfer by visualization. We can observe that our approach possessing adversarial transfer learning makes the two distributions of the extracted features much closer. In summary, we focus on the task of named entity boundary detection. We proposed AT-Bdry, an end-to-end neural model to detect entity boundaries from text without any handcrafted features or any prior linguistic knowledge. Our approach incorporates adversarial transfer learning into a novel sequence labeling model to encourage domain-invariant representations. It is without requiring any annotated target domain data. If you have any question, please do not hesitate to contact the author via this email.